All right, ladies and gentlemen. Now for something completely different, we switch gears and go from proteins to small molecules, and we will talk a bit about non-targeted metabolomics, but you will notice pretty quickly that many of the things that we've discussed this morning will be reasonably similar to what we're going to be doing with metabolites. In the end, it's all doing mass spectrometry. So when we compare the metabolome and the proteome, we had this discussion yesterday already. The size and the complexity of the metabolome is really not well defined and largely unknown. We have really no idea how many metabolites to expect in a specific sample. There are also no metabolite databases that really list all potential metabolites. Yeah, we find small molecules everywhere, but someone said it already, there's a potentially infinite number of these molecules, and we can't really be sure how many there might be popping up in this or that metabolomic sample. What we're pretty confident is that there are tens of thousands of known metabolites that have been seen somewhere, or we have some idea of what their role is. There are other differences between the proteome and metabolome that one should at least discuss briefly. Metabolites have a much wider range of potential chemistry. There are different elements that show up. Halogens, for example, are suddenly an issue. Proteins have, in contrast, a much more homogeneous chemistry. And where will that be an issue? Well, when you think back to what we discussed this morning when we were talking about the average gene, that is one of these hypotheses that no longer holds for metabolites because they can have a much more diverse chemistry. Also, it's much harder to really talk about metabolites. We can't just write down the sequence. We would have to write down the structure or the name or some ID. It's much harder to talk about metabolites than it is about proteins in that respect. Then there's a key difference, and that is just the weight. Metabolites tend to be small molecules. They tend to be lighter than peptides, usually 100 to 300 Dalton. I mean, I'm not excluding anything heavier here. Again, that's a very fuzzy boundary, but on average, they tend to be lighter than the peptides we see in shotgun proteomics. When we discuss metabolites, then it's basically everything that we can observe in a biological system except salts and except macromolecules. So anything goes. That's basically all metabolomics. Lipids and sugars fall in that category as well, but are not always considered part of the metabolome. That's what we got lipidomics and glycomics for. And you can also look at what is known about these guys. People have tabulated metabolites in some biological systems. That has been in the textbooks for a while. You see there's plenty of structures. We have different concentration ranges, probably as large in dynamic range as we see in the proteome. But again, since we don't know much of the metabolome, it's hard to really make a clear statement there. Similar to proteomics, we also have different types of quantification technologies. Labeling doesn't play such a large role, and that is pretty obvious. If these structures are all over the place, then it is not easy to come up with one labeling reaction that sort of captures a large portion of the proteome, even though in GC-driven metabolomics we use derivatization a lot, but that is not labeling as such. In metabolomics, actually, to a larger extent than we see that in proteomics, we distinguish targeted and non-targeted approaches. And targeted metabolomics aims at identifying a well-defined subset of the metabolites, often with high accuracy, but only a small subset, hundreds of metabolites. There are kits, there are companies that sell them to do that. There are different approaches for doing that. All of these metabolites are then automatically identified because you go in there in a targeted fashion, you know what you're looking for. That can be interesting, but it's a very narrow view, and it often covers only specific aspects like central carbon metabolism, parts of fatty acid, amino acid metabolism. And if whatever you're after is not really part of this small hole in the metabolome that you look through, then you will just not see it. If we're talking about non-targeted metabolomics, that is also called by some metabolic profiling, then we have another problem. We see lots of things all over the place, but we have basically no idea what they are. When we compare identification, and we will talk about that tomorrow morning, then metabolomics is far behind proteomics. It's just much harder to identify metabolites. Metabolite quantification, however, that is something that we understand reasonably well. It's basically the same idea that we discussed this morning. Label-free proteomics is very similar to non-targeted metabolomics. The overall workflow is basically the same. We do some feature finding. That is the key difference. We need to do the feature finding in a different manner. We do the map alignment, we do the feature linking exactly with the same tools and the same workflow. That is really straightforward. Feature finding approaches are algorithmically similar to what we do in proteomics, but the algorithm I'm going to present here, that is the feature finder Metabo in OpenMS, works in a slightly different way than what I presented this morning for proteomics. It's sort of a different evolutionary stage of this algorithm that was published a couple of years back. The key differences between these algorithms are that the isotopic patterns are very different from metabolites. Different mass range, but also different elements, different composition leads to a much broader range of potential patterns. And the mass range and charge states are very different, and that requires some adaptation as well. So let's look at that, and this is going to look very familiar. I just took the slides I had this morning. You've seen that. We use the same terms. A map is a 2D data set. What are the differences between maps in metabolomics and in proteomics?
One's peptide, one's small molecules.
Yeah, that is one aspect. Yeah, so the patterns will look different, but the chart states are different. But they will be smaller, yeah, because we usually run shorter gradients for metabolites, where we use a couple hours in proteomics. We usually get away with 10, 20 minutes in metabolomics. And we have a narrower mass range. Rather than going up to 2,500 Dalton, we go up to, say, 1,000. And that gives us a better resolution. Remember what I told on the first day. If you have more resolution in this narrow range, you can also start seeing this isotope fine structure for metabolites in contrast to proteomics. So there are a few differences, but ultimately that's still what it looks like. And we use the same overall schema. We try to find features in all maps, reduce all these peaks to features, align these maps, link the corresponding features. And now, again, we want to identify, and that is no longer a sequence, but that would then be a structure, like carnitine in that case. And we want to quantify, we want to get relative intensities of these features across the maps. Okay, so far, so easy. Yes? You can, and it depends a bit on the application. But give me a second to go through that. In proteomics, we have been using this averaging hypothesis for many things, but since we can't use that, we have to come up with something that is a bit smarter. I will show in a minute how that is being done. It turns out that machine learning is an approach that can be employed here. We don't have an underlying model, but instead we learn to recognize what what a feature looks like, a metabolite feature, and that is a bit more flexible, although it requires some training. Another problem that we see with the proteomics feature finding algorithm was that we have lots of parameters playing around with them. You might have noticed there's quite a few parameters. In an ideal world, the algorithms would get away with a lot fewer parameters for the algorithms. You will see that we did that here. Also, the sensitivity can be problematic because this lack of sensitivity, as we discussed earlier, can lead to missing values, and that might be problematic in downstream analysis. What is typically being done in proteomics is, in metabolomics, is a feature finding that has been around for a while. I will give you some idea of what other tools do. If you've worked with metabolomics data, you might be familiar with XCMS. That is actually an R package, a bioconductor package written in R, where the key idea is to extract these mass traces in a very straightforward way. They do that by binning. So they basically take the spectrum and everything that is in a certain mass interval, they throw that in a bin, and then you have adjacent bins, and this way you basically get vectors. You discretize these spectra, and you can then detect peaks in adjacent bins across one mass range using standard chromatographic peak detection techniques. You can align these mass traces in the RT dimension using some non-linear dewarping. That works reasonably well. There are a couple other things that are being used: filling in missing data, matching across samples, retention time correction. You see they do it in a slightly different way, a slightly different order as we do it. And since it's all embedded in R, it is sort of very convenient to also do the statistical analysis in R, whereas in OpenMS, you either embed your R code into KNIME, or at some point you just export it into R and go from there. No? So XCMS in the original version does not consider the notion of features. Instead, you will actually get different mass traces, and you will get multiple mass traces for the same metabolite. And that's a bit of a problem. There's another R package that can be used to post-process that is Camera. And Camera goes over these mass traces and figured out what should go together. The way this is done, you see, this is what such an extracted iron chromatogram looks like. And you know, the binning is already part of the problem, because binning is not a very stable process. This is why one of the reasons why these chromatograms don't really look all that nice, because they are often split across adjacent bins. Yeah, and XCMS tries to fix that by combining them again. But ultimately, this discretization is a bit of an issue. And then you can do peak detection that is done with wavelet techniques, for example. And then you figure out that, yes, indeed, here there is a peak. So they're basically detecting chromatographic peaks in these bin spectra. It's basically extracted iron chromatograms that they look at. XCMS has become sort of the quasi-standard for LCMS metabolomics data analysis, and in recent releases that has been improved in many ways, also adding Camera to assemble features. Then we started with a very different view on this because we came out of proteomics and we had this notion of a feature, and we didn't understand why everyone was just looking at peaks, chromatographic peaks. So instead, we thought we really do it the same way we've done it for proteomics, and we really try to assemble these features. But we started with the same idea. You remember in proteomics, since we started out with low-resolution data, we tried to match this overall shape independent of resolution. In metabolomics, we started with high-resolution data straight away. That is why the algorithm has a different characteristics and different way of going forward with it. What we wanted to avoid was this discretization in bins. because it's sort of didn't appear natural to me. Instead, when you look at these spectra, you see which of these peaks are aligned, but you don't have to discretize in specific bins. So instead, what we try to do first is a mass trace detection, and that is not based on any discretization. I'll show you how it works in a minute. That has a few other nice features. It tries to collect all the peaks that are in adjacent spectra, and it aborts. Well, you would see when it aborts once we are running out of the feature, and there are a couple of criteria to detect that. Then we try to find isotopes by looking at mass traces that we have found that are adjacent, that are in the right distance, that are co-eluding, that have the right isotope ratios. And once we have identified that these three guys belong together, we reduce all these peaks, or these mass traces, I should say, back to one feature. So we say this here is a feature, it has a certain retention time, it has a certain mass to charge, a certain charge, and a certain intensity. And that, again, is our data reduction step, and then we repeat that for all possible mass traces that we can find. The way this is done is that we are looking for mass traces by starting again at high intensity peaks and then working our way down. I will introduce that algorithm in a minute. It's based on a Gaussian kernel density estimator. These mass traces are basically just collections of peaks at this point. So we just say in this spectrum, all the peaks that are in this range, in these spectra going from here to there, that's one mass trace. And then we have the same issues that we see in proteomics as well. We can have lack of baseline separation of these chromatographic peaks, in which case we need to cut the feature. See, we then cut these mass traces in half at that point. We need to make sure that we assemble the right mass traces. We use the distance primarily, but also co-elution for that. And in the end, we end up with something very similar. And we can also visualize that in top view in the very same manner. So the data will look more or less the same, independent of whether you do proteomics or metabolomics at this level. It's very similar. How do we detect these mass traces? That's actually the most interesting part of this algorithm in a way. We define first of all a peak. P is a triple. It has a retention time, a mass to charge ratio, and an intensity. And the mass trace T is now just a list of these peaks. And these peaks should have similar mass to charge ratios, but not identical due to the measurement error that we have. And of course, these mass traces should be ordered peaks. They should not be all over the place, but they should actually be in contiguous retention time slices. The question is a bit, when do you start collecting peaks and when do you stop collecting peaks? That is at the heart of that. I would like to give you an example. You see these dots here. These are all peaks that come from one mass trace. You have mass to charge ratio here and retention time there. Now, when you look at that, I can tell you that this here is the highest peak, and you can believe that or not. What is a bit perhaps not obvious when you look at the data for the first time is they have more or less the same mass to charge ratio here in the middle, and then they begin to scatter. Why is that?
Sensitivity, the number of counts you can get in the
Yeah. As you go down, it becomes harder to spot the peak, and it becomes harder to call the apex of the peak. So it will actually, the mass accuracy of this mass trace goes down as you approach the noise threshold. And that is interesting because it kind of tells us when we can stop collecting peaks. So what we actually do is we start with an estimate of the error that can just come from the instrument. You ask your experimental guy who runs the mass spec, what's your mass error on that instrument? He'll tell you, don't know, 1 ppm. And that's good enough estimate to get started with. But actually, in this local region where we're looking, this mass error is much, much lower than that. And we will make use of that to assemble these mass traces. So what we're going to do is we are using online Gaussian density estimation. It's basically computing the local error, standard deviation, online, and updating the error as we go along. And that is quite straightforward. We start with one peak, and these error bars indicate our nominal mass error. That is what we start with. That is what we should expect from the instrument. Now, we check for peaks to the left and to the right of that mass trace and check whether they are within this error bound. In this case, yeah, that's true. We add this peak to the mass trace. Now we have two peaks. Now we can start adjusting this error. So this error is going down because we see, no, they're not 1 ppm apart. They're just 0.1 ppm apart because the mass accuracy is very high. We have high intensity peaks there. They are well picked, and that helps us to figure out how far we can go, because we just keep on adding these peaks until back here, when these peaks start scattering around, we say these are no longer part of our mass trace, and we have an accurate estimate of the mass error within this mass trace that is much better than a nominal instrument accuracy.
So you predefine this, this sigma, like 2 standard deviations now away from your error, as what you call it, outside of the
Yeah.
Maybe, aren't you losing things that are within the instrument error, but you lost them because you restricted the domain?
Yeah, and that is the idea. Because the instrument error is an overestimation of what we have locally. So the idea here is really to find a mass trace where the error that we estimate is consistent with what we see on this mass trace. Yeah? So it's basically it aborts once the data it sees becomes inconsistent with its internal error model. Yeah? And that's sort of the beauty of that, because you end up with a mass trace where you know exactly what it means, and where this abort criterion is basically intrinsically defined by the data. And that makes it very robust. When you start with this error window, it doesn't matter whether you start with 1 ppm or 2 ppm. It just has to be a decent estimate. If it's too narrow, then that's not a good idea. But if you're off by a factor of 2, it doesn't really matter. It will still end up with more or less the same mass trace because it estimates this error on the go. It just needs a decent starting value.
So this error will never get smaller with time, like the estimation.
With what do you mean with?
The online estimation of the error will never increase.
No, no.
So just to reconfirm, you use the 2 sigma for every local error?
Well, we update the sigma with every step.
Yeah. So like the sigma is iterated over, but so between like the highest or the lowest point, like so as soon as it's outside of 1 sigma?
Yeah, so as soon as it is outside of the estimated error, then we no longer add to the mass trace. So we abort the search on the left and on the right.
So would you not account for how instruments have a higher error bias in like the lower mass ranges?
That is where we abort it, because we say that is how we detect that we shouldn't be looking there anymore. So we're not going all the way into the noise. We're going into the noise,
No,
but not further.
intensity, I mean mass
Oh,
charge
you're
range.
talking about ppm error.
No. So also, don't you have a higher ppm error
Right,
bias in
and
the
the-
lower mass ranges?
Right, but that's
That's why it's in ppms, because
Yeah.
it's a relative mass error. Yeah, so it's not an absolute threshold. It's a relative threshold.
so this technique would be very sensitive to contamination or dirtiness of the mass spectrometer. If you have a lot of noise, then obviously your sensitivity of these peak measurements goes down. So you'd be artificially cutting off your sensitivity measurement compared to
Well, you will see in a minute that it's way too sensitive still. So it works reasonably well. it just has some issues. If you have mass traces that run over the whole length, it's going to pick those up as well. So there are a couple issues that are still problematic, but on the whole, this is probably the most robust way I've seen to pick mass traces. Once we have these mass traces, then we apply similar techniques as XCMS to detect peaks on that. So we basically try to figure out whether our mass trace is clean. And that is where these long mass traces become problematic, because you can still have features on them on top of this baseline level. And then that's a bit tricky to figure that out and then sort of disentangle that again. Now we have to assemble these features. Now, as I said, we don't have an average gene hypothesis. So in contrast to what we can do in proteomics, where we test these hypotheses, that trick no longer works for us, because we would discard the majority of these isotope profiles. They will have very different intensities. So what can we do? We can still hypothesize what should go together. We just need a different type of scoring function. So it's no longer just a mere fitting, but we use three things that we know about these features. First of all, the mass traces that belong to the same feature should all co-elute. So when you look at the mass trace, there should be a high correlation between these mass traces. That is straightforward. The second thing we know is the mass distance. We still know that they should be apart by roughly the proton mass divided by the charge. So you can do that, and actually now we have much better mass errors than we had in proteomics, because we estimate these mass errors on the mass traces themselves, and that narrows down the options of how to combine these mass traces drastically. So we have a scoring function there that just looks at all these distances and then assumes a normal distribution for the error and scores it accordingly. And if they have exactly the perfect spacing, then they get a high score. And if they deviate for whatever reason, for example, because the mass trace has too low intensity and thus wiggles around, then it gets a lower score. The retention time scoring is actually very similar. We basically look at the shift between these mass traces, and we use again a Gaussian error model that tells us how likely it is that they actually do co-elute based on what we've seen. Note that we are not using a peak model there. So we are making no assumption about the shape of the elution profile at this point. Because we see that in metabolomics, the peak shapes are often even weirder than what you would expect in proteomics. And that has a nice side effect. You can also apply that same algorithm to data from, say, capillary electrophoresis, where you have peaks that are basically rectangular. So it works well, and you don't have to have any assumption on the peak shape. You just have to have a rough estimate of how large your peaks are. And again, the algorithm is pretty robust. Whether you're off by a factor of 2 or 3 in this parameter, that won't matter. The next interesting thing is actually, how do we deal with the intensity distribution? Averaging doesn't work, so what did we do? We enumerate all metabolite compositions. And there is something that was an interesting idea that's called golden rules. It was published by Kind and Fien already 10 years ago. And they allow us to generate all possible compositions of a large chem space. And the composition is enough. Yeah? We don't need to know the structure. We just need to know the compositions, because for the same composition, we would get the same isotope profiles, of course. And what you then can do is you just generate 24 million of those. You randomly subsample, and you just start learning the patterns that you have seen. And we basically trained a support vector machine, a one-class support vector machine that just recognizes metabolite patterns. It's kind of a detector that says this looks like a metabolite and that doesn't look like a metabolite. It's a very straightforward thing. It then integrates that, so we put in the intensity ratios that we have from the mass traces and ask the support vector machine, does that look like a metabolite or not? And since it has seen all these possible combinations of isotope intensity ratios, it can more or less confidently say, yeah, this looks like something. Even though the ratio might be weird and you wouldn't expect it, it might have seen that in the data set already.
What is the SPM like error rate?
It's I don't know the number, but it was 90-something +%. So it's got a pretty decent error rate. So we see very few losses due to the intensity variation. Yeah. No, it's pre-trained, but yeah, of course you can retrain it if you like, but it's pre-trained. Yeah. Okay, so how well does that work? Quantification is not that easy to quantify, but there are a few measures that work okay for that purpose. So what we did here is we simply took a plasma matrix and we spiked in 2 drugs, reserpine and terfenadine, at various concentrations. You see it covers quite a range. And as you can see, the linearity of that is the feature intensity that was extracted from this feature finding algorithm as a function of the stock concentration that was put in. And we got R squared of 0.997, 0.998, so that looks quite decent over about 3 orders of magnitude, 3.5 orders of magnitude. But we had these questions of sensitivity and specificity early on, and that is much harder to quantify in a way, because technically we don't have a ground truth. So even if the feature finder detects something, you cannot be sure what it is, and you cannot exclude that it's not really there. When we first looked at our results, and you've seen this bathtub curve already before, we compared ourselves to XCMS and camera. So this here again is the number of measurements where that was found. We had 33 runs that were basically technical replicates. And we were looking at the number of detected features. So the first thing that we were happy about is that here we had twice as many that were consistently found. And now you could argue, well, but this here is scary. That means it's just false positive. It's just picking up stuff. Could just be hallucinating features. Or it could be that XCMS is for the low intensity stuff not as sensitive as we are. And actually, from experimental data, you have no way of knowing which is true. I mean, you can look at the data and say, yeah, I believe this or I don't, but you have no way of really knowing what's true. So we did something that got us into quite some trouble with the referees. Yeah, yes, please.
Does XCMS include all peaks in there? But because you classify as features, but XCMS doesn't have features? So
well, that's why it's XCMS and camera.
Camera will join the...
Yeah. So what we proposed instead is we just generate synthetic data, simulated data. For computer scientists, that is normal behavior, but for many referees that came from the experimental field, that was an absolute no-go. That is why we also included real data. What did we do? We basically have code that simulates LCMS data. And we took a composition out of a plant metabolite paper that had meticulously listed hundreds of thousands of metabolite compositions that they had found. And the composition and the retention time, that's all we need. Because if we have that, we can go out and simulate the spectra. We can put noise on that. The simulator has different noise models. And the good thing is you have now a ground truth. There's nothing in there except noise that doesn't have a feature behind it. And then you can start doing a more thorough statistical analysis and start asking questions about what is the precision, what is the recall of these methods. So do we actually hallucinate features? And at least on the synthetic data, and I will not get into this debate versus simulated versus real data, on the synthetic data at least we could show that the recall and the precision of the OpenMS feature finder is above 96%, which is quite decent. And we actually see that XDMS here has a lower sensitivity, so it does indeed find fewer things, and that is what we are quite happy with. We started believing our results, even though still there might be some issues. Now, how does it look like in OpenMS or in KNIME? Metabolomics workflows tend to be reasonably complex. What you see here, obviously you can't read all of that, but that is one workflow that we designed for a diabetes metabolomics study. All in all, it has about 150 different nodes in this workflow, so we colored them. There's some data processing, that's the basic metabolite quantification workflow here in yellow. We have some quantification or downstream quantification in purple. We have identification based on accurate mass and database search up here in gray. That's what we will discuss in more detail tomorrow, how that works. And then we have various downstream statistical analyses, machine learning tools that were used, visualization that was used to really distinguish what we see. And here it comes in handy that KNIME was originally designed to work with, for cheminformatics, to work with small molecule structures. So KNIME has this built-in visualization of structures already. And that makes it very easy to then also give us results list where we can see the structures of these identified metabolites. So let's look at some parts of this workflow. This will look very familiar. In order to do non-targeted metabolomics, we have basically the same workflow that we had for label-free proteomics, except that this node here is now a different feature finder. That's feature finder Metabo, but the rest should look very familiar to you. We're just doing alignment linking, and then we export that as a text file. It's a tabular file that goes into the downstream analysis. And in the simple example here, we were running 5 controls and 5 samples, and you can look at the parameters of this feature finder, and there are few parameters in here, and that is by design and not accidentally. We basically made the internal parameters dependent on 2 key parameters, and that is the mass error in ppm that you expect and the chromatographic peak width. There are a few auxiliary parameters, but that you usually don't need to fiddle with. But if you know how wide your peaks are, and if you know what the nominal mass resolution is, then you're fine with this particular algorithm. Now, what falls out at the end of this pipeline here is then a table that contains everything you need to know for the quantification. You have a list of features, feature 1 through n. You have the centroid retention time, mass to charge ratio, you have the charge, and then you have columns per sample. Every sample simply has an intensity value or has not available if it couldn't be found in this particular map. And that makes it very convenient to sort of do downstream statistical analysis of this. You can go directly into R with it, you can export it to Excel, you can do whatever you like. The only thing that is missing at this point is, of course, the identification. You don't know what it is.
So why? So can you just apply this Metabolome finder, peak finder to your proteomics data? Or?
You can, and we've done it. It will not recognize these these peptides as metabolites. Shorter peptides, yes, but longer peptides have isotope profiles that look very dissimilar. So we actually have a version that we have been using that has an internal averaging model, and that works okay as well.
But is that because of the peak training model that you used?
Yeah.
Yeah.
Oh yeah, of course. But there actually you don't need to train it. Yet you just plug in the averaging model and you're fine. Okay. What follows in this workflow, just to give you some flavor of what you can do, is some table magic. So we rename the columns, we split them in various ways, we handle missing values in various ways. So we just apply that to this table to get rid of some of the issues that we had. Then we do some R magic. This is where the intensity normalization happens based on, again, background intensities. Here we do statistical hypothesis testing to see what is really differential, and then we visualize that. And it turns out you don't need to identify that many metabolites. In this diabetes study, in the end, we had 17 features that were really statistically significant. And then you can just send the RT M over Z to the guys in lab and ask them, well, look at the spectra and figure it out. I don't really care what it is. It's your problem now. What? I don't recall the number, but tens of thousands, I think. Round about 10,000.
So the intensity normalization, you use the same factor where you're looking for stable analytes and you're just taking area?
Yeah, here the R does some more magic, but yeah, it's basically background normalization. And in KNIME, you can now hook up plots to all of these steps so that you can actually do some sanity checks in all the steps as you go along and get plots out of that. You can construct the box plots for these. So this here looks at the various samples and tells you that indeed the normalization worked well. You have an intensity distribution that is even across all samples, so that gives you a warm, nice feeling that you got it right. And then you end up with few things that you need to identify. And that makes it a lot easier. That is why we try to quantify first for the most part in these metabolomic studies, because in the end what you need to identify is probably not the whole world. Identification itself can be done with multiple strategies. Again, we will discuss that tomorrow, but to give you some idea of how it is done, of course, just sending the retention time mass to charge ratio to your collaborators is one way. That's the easiest way. But you can also generate a table that gives them some hints of what is going on. How can you identify metabolites? Well, the easiest way is you just look at the accurate mass. Accurate mass, not the exact mass. Yeah? But you compare these accurate masses to the exact masses that you have in databases, and that can be done by just entering this mass into an online web server and see what pops up. You can also do spectral matching. If you have tandem spectra that are associated to a particular feature, you go into a database with that, or you have your local database. Many of our collaborators also have spectra that they have measured, that they have manually identified. They usually have a couple hundred or 1,000 spectra, and they're sitting there, and we just match them and say, yeah, this looks like glucose. You've seen that before. And these labs can then add to this spectral database everything that they identify or whatever they find that's interesting they put into this library. And that can be done like this as well. You see there's a metabolite spectral matcher that takes basically a database and matches against that, and all these different lines of evidence can then be merged into one table. And this is where drawing these structures comes in handy. This here is now a table view in KNIME, and you see all these different hypotheses for the different features. You can browse through them, and you can give that the whole workflow, including this analysis, to your collaboration partners and tell them, go through the structures, see whether they make sense, check out the spectra if you have questions, and it's all in one workflow. All right, that's all I have to, yeah. No, MS2. It's based on fragment spectra. From MS1, you would take the monoisotopic mass and you would do an accurate mass search in database.
You have something like a calculation for predicted retention times versus actual retention times?
Yes, we do, but it's not a tool that we have right now. We've been toying with it for a while. In my experience, the added value is rather limited. Because, and when you think about it, it's pretty evident why that should be the case. Although we've published papers on it. We've published a paper on lipids, we've published quite a few papers on retention time prediction. The added value is rather small because if you have two structures that are isomers, and where you can't distinguish one from the other, then oftentimes they will also have very similar retention times. And the error bounds that you can get on retention time prediction are not that narrow, also due to the reproducibility of the retention time, that they will be able to distinguish these very closely related isomers in the majority of cases. So yes, you can basically cull your list of 50 structures down to 40 through retention time, but it's not going to bring you from 50 to one structure, because the error bounds in the prediction, even when you work really hard, are going to be on the range of about 3 to 10% of the overall gradient time. And that is too wide a window to really see much of a difference.
Based on this, you don't really use data as part of the normalization.
No, not for the normalization. We would use that type of normalization and that type of plot for the QC.
Yeah, to see if there's anything
Yeah.
really wrong.
Yeah. But the QC workflow is not part of this quantification workflow. We usually do that independently. And back at the time when this particular study was done, we didn't have the QC workflow in OpenMS yet. All right. Further questions? No? Then I won't keep you from digging in and working your way through the tutorials, and I'm still around for questions.